Okay, so let us continue with the next topic. The properties of the fluid again. That now we are going to discuss with the fluid known as liquid helium. So next fluid is the helium. So the is an, as you know, is a chemical element. It's having a symbol as He. Then atomic number of helium is 2, He2. Then we used to term as atomic number is 2. Again, it is a colorless one, odorless one, tasteless one, non-toxic one, but is inert gas, monatomic gas. Similarly, in the periodic table, the gas availability is in the form of noble gas group. They are also known as noble gas. So, compared to all these fluid, what we are under discussion, like hydrogen, oxygen, nitrogen, helium, and air, this helium is having a extremely very low temperature. This is the lowest temperature among all the other elements. So, unlike other elements, this helium will remain in liquid state down to absolute zero at normal pressures. That is one of the important property of this fluid. The fluid which remain in liquids down to the absolute zero temperature at normal pressure, that is nothing but helium. So start with helium 1. So we have discussed different variant of helium. Start with helium 1. Helium 1 is boiling point is 4.22 kelvins. Below this boiling point 4.22 is they are all cryogenic fluids, and above the lambda point 2.178 kelvins, the isotopes helium 4 exist. So we have again helium also having its own isotopes. Helium 2 4, that is helium 2 with 4. The helium that is called the helium 4 is exists in a normal colorless state. The index of refraction 1.06, one more property that is under discussion for helium. And density of this fluid is 145, range of 145 to 125 kilogram meter cube. The temperature range 0 to 4. If it is 0 Kelvin, it is 145 kilogram meter cube. If it is 4 Kelvin, it is 125 kilogram per meter cube. So that is some property of helium 1. The second fluid, that one is helium 2. That the helium below its lambda point, called helium 2, exhibits very unusual characteristics. That thing is, it has its high thermal conductivity. When it starts to boil, it does not bubble, but rather it evaporates directly from the surfaces. Like unlike other fluid gases, if you are keep on changing this conductive because of the conductivity problem, thermal conductivity problem property, when it starts boiling, it does not bubble; it will directly evaporate from its surfaces. Since the fluid is also known as superfluid. So already yesterday we were talking about supercritical and superfluid and other systems. So this fluid, the fluid helium is known as superfluid. This fluid is known as superfluid. But when it will be superfluid, that is only at lower temperatures. If the temperature increases, it cannot be superfluids. But on only at the lower temperature system, it will be superfluids. The helium 2 is the superfluids. With have its higher strong, very strength. Its properties are very strength properties, and these quantum phenomena are also known as macroscopic phenomena. For an example, when it flows through a thin tubes, it has no measurable viscosity. The measurable viscosity is negligible. If you are measuring this helium and fluid, when it passes through a thin system of meter size of 10 power minus down to minus 8, or minus 8 meter size of the capillary tubes, the viscosities are negligible. It cannot measure. It has no measurable viscosity. So the temperature required, if you want to produce the liquid helium from the helium gases, the temperature required to produce this helium fluid is very low. That's why we discussed the boiling point of the fluid at lowest temperature. The reason began that is because of the weakness of the attraction between the helium atoms. The atoms, helium atoms, they are very weak. The atoms, the gases, personally the helium gases, the atoms present in the helium gases are very weak. We can able to easily you can able to make it in the form of liquid heliums. Similarly, since the attractions between these molecules are very weaker, or weakness of the system causes the interatomic forces also very weak. The reason behind that is the helium is a noble gas. If the helium gas is a noble gas, that interatomic forces also very weak. Similarly, the boiling point and critical point of this helium, helium-1 and helium-2 and helium isotopes depends on the helium isotopes. These properties also differs. So you can see, as I told you about TS diagram of general fluid, already we shown to you, but you could able to see the diagram. See there you have number of isobars. So the red color line, the curved lines, the parallel to all the curved lines are it gives idea about the isobar. It's a constant pressure curved line. So again, as I mentioned, we have a point temperature correspond to on y-axis that the point maximum at that under the point is given as point is called as critical point. That value is 5.2 Kelvin of this helium property chart. It's a TS diagram chart of helium with all the temperature scales. So this can be useful for while designing a cycle which operates on Linde or Clad or like Hepits or any system of engines. These charts will be useful to identify or locate the points or the property, locate the property at the stations of operations. So as an example, you see, it is given on 1 atmosphere, 4.2 Kelvin, is boiling point of the helium. You see that from that point, below the point, it is all in liquid state. So already told you, we have this side is all a liquid state side. Other side is under the curve or a liquid plus vaporized side. After the point, it is becomes vaporization. So the critical point, the point above which it will be becomes supercritical fluid. So they are called the supercritical fluids. So under this are all normal cryogenic fluids. So 1 atmospheric and 4.2 Kelvin is correspond to the boiling point of the helium. That is the cryogenic fluid system. And correspond to the critical point of this system, that value is 5.2 Kelvin. That correspond to 2.2 atmosphere. So the red color, the whatever curve parallel to the red colors are known as isobar curves. The x-axis value, if you project the points towards x-axis with respect to the isobar, with respect to temperature also, we can able to fix the entropy correspond to the station location where the operation starts, where the cycle starts. So once temperature and the corresponding pressure at the particular operating point known to you, if you go and check with the helium, you can able to find the helium properties. Similarly, for hydrogen, oxygen, we will be having the same kind of charts. These are all called as TS charts or TS diagram of these gases and the fluids, liquids. Then it is fluid and liquid. All the temperatures are available. So below temperature also available, above temperature also available. We can able to fix the critical point. We can able to fix the triple point. We can able to fix the boiling point. All the properties can be found, which can be useful for designing a general cycle, operating cycle for the generation of these fluids or working with the any systems. Similarly, that we may parallel similar to these charts, may have also have the tabular data also for which each every temperatures corresponds give the tabular data of these cases also is also available in the textbooks. So the charts and textbook you can able to find out from your internet sources or the various textbooks or reference books or the ebooks available in markets. So you can refer it for understanding the ideas. So coming to liquid helium. So liquid helium, the helium exists in two isotopes already I already told you. So we have helium-4 and helium-3. There are two isotopes. One isotope is helium-3, other one is helium-4. So 4 means 2 electrons and 2 protons and 2 neutrons. 3 means 2 electrons and 2 protons plus 1 neutrons. Proton and neutrons is 3. Protons and neutrons are 4. Based on that, we have atomic mass and atomic number. What do you mean by isotopes? Anyone? Anyone answer the question? What do you mean by isotopes? Anyone?
So elements with different number of neutrons.
Hmm. Same number of
Protons.
same number of protons, different number of neutrons. Correct. Okay, same number of protons, different number of neutrons. Can you define in terms of atomic number and atomic mass?
So atomic number remains same.
Hmm?
Atomic number remains same.
Atomic mass difference.
It's
Right.
different, yeah.
Okay. So that is isotopes. So like that, this helium, like normal helium gas, this liquid helium fluid also have its own these two fluids. Then next is the phase diagram. So already we are discussing on phase transition, first order, second order, and phase transition, and that and heat, everything we are discussing. So now we are going to discuss with the phase transition of a phase diagram of this helium systems. So helium has no triple point in general. That means there won't be coexistence of solid, liquid, and gaseous phase occurrence in terms of a helium gas. That's why doesn't have any phase coexistence of the system. There is no. That's why that doesn't have any triple points. So we have a liquid helium. Already you know the saturated liquid or saturated vapor ion systems. So if you go for compressing with the 25.3 bar, then it becomes solidifications. So we have see the diagram with solid, liquid, and vaporized regions of system with respect to temperature 1, 2, 3, 4, 5, 6, 7. Increase in the temperatures or increase the process. That first area covers the solid phase and other area with respect to liquid and vaporization. So when keep on decreasing the temperatures, the liquid helium tends to be liquid helium 1 at the beginning, then it becomes liquid helium 2 at the end. So that is the thing given in the chart. You could be able to understand that changes between helium to helium 1 and helium 2 for different phase transition with the solid, liquid, and other vaporization systems with respect to temperature and pressures. So if you want to solidify this liquid helium, you have to compress it with respect to pressure or range of what I call 25.3 bar to solidify this system of this helium system. So the if it is helium is cooled below 2.17 Kelvin, then it becomes liquid helium 2. That's why we have liquid helium 1 and liquid helium 2. So liquid helium 1 will start with helium, then we will liquefy and it becomes 1, then below 2.17 becomes 2. So these two fluids available in with respect to cryogenic fluid of called as cryogenic liquid or helium or liquid helium 1 and liquid helium 2. They can be distinguished based on these viscosities. So this it is liquid helium is normal fluid, and liquid helium 2 is superfluid. So just now we were discussing on while it passes through the capillarity in the tube of 10 power minus 7 to 10 power minus 9 type of tubes, the viscosities cannot be measured with this fluid. They are called as from fluid. So based on this viscosity availability or viscosity measurement on the range of viscosity, these two fluid, liquid helium 1 and liquid helium 2, they are termed as normal fluid and superfluid. So the helium 1 is normal fluid and helium 2 is superfluids. So start with the helium 1, helium then becomes helium 1 with respect to reducing temperatures. And further reduction in temperature of 2.17 Kelvin, it becomes liquid helium 2. So up to helium 1, it is the normal fluid, and below that, the 2.17, it becomes helium 2. They are termed as superfluids. So that's why the helium 2 always known as superfluid helium. So just now we were discussing a lambda point and lambda line and all. I just to tell you what is the lambda line and lambda point. So you could see the phase separation. So first order transition, second order phase transition, and the phase separation. The line which separates the phases, they are known as lambda line. See the diagram. We have liquid and we have solid and vapor. Between liquid and vapor, one line is there. That is line is called the lambda line. The point correspond to that line is that is correspond liquid and solid and vapor. That transition is called the lambda point, and the separation line is the lambda line between these two separate phases. The point of intersection of this phase separation line as well as the saturated liquid line is called as lambda point. The line is saturated liquid line. One line is liquid line. That is called saturated liquid line. Other one is phase separation line. So that these two joining point is called as lambda point. The slanting line black color is lambda line, and the red color and the solid transition with respect to the intersection of this black and red that correspond will be gives idea about the lambda point. That viscosity is zero viscosity, as I mentioned earlier. It cannot be measurable if it passes through the super capillary tubes of a very thin fluid, thin tube. It cannot has not have no measurable viscosities. They are known as zero viscosity systems, but the conductivity is large. They are called as superfluid. That is called liquid helium 2. This superfluid can expand on cooling. So whenever cooling this fluid will expand. So below the 2.17 Kelvin, it becomes superfluid. That is liquid helium 2. They are under expansion during this cooling process. The point is known as lambda point. See the diagram, it looks like a lambda, normal lambda symbol. That's why it is the line is called the lambda line and the point is called the lambda point. So the point is called the lambda point because the shape of the core resembles the Greek letter lambda. So during this lambda transition or the phase transition, there is no energy involved. The specificity is infinite at point lambda point. That is second order transition. That's why I asked you the question. I asked you to find out the difference between first order and second order transition. The answer is available here. You see there. Second order transition is have its infinite lambda point. That is always having no energy involvement. There is no energy involved. That specificity is infinite. That point is system is called as the lambda point is known as second order transitions. But first order transition involve latent heats. But second order transition, there is no energy involved. That's the answer for this difference between first order and second order transition systems with respect to discontinuity and continuity. The variation of this specific heat in the liquid helium is very abrupt. Again, the answer is available. Discontinuity is possesses a discontinuity. So second order transition or second order fast transition occurs discontinuity. So that's why I asked you yesterday itself what's the difference between first order and second order in terms of discontinuity. So second order is having discontinuity, possesses a discontinuity at this point lambda point with respect to lambda transition line and the intersection of lambda line and the saturation liquid line. Since the viscosity also no measurable viscosity with respect to the thin tube of flow through the thin tubes, they are called as superfluid. The temperature range is 2.177 Kelvin. Below that one, the line represents the Greek letter lambda. That's it is called the lambda line. So the speed cat is in specific heat is infinite, and there is no energy involved. The discontinuity in the lambda point processes the discontinuity. They are called the second order transitions. So already mentioned viscosity for the flow through a thin channel, very thin tubes or thin capillary it is only the function of temperature or it is very independent of the temperature drops. So these are all about the transition across second order transition in the superfluid helium. So as I already mentioned that the helium fluid is comprises of two fluid. One is normal, another one is superfluid. So normal fluid is liquid helium 1, superfluid is liquid helium 2. Below 2.17, it is Kelvin, it is a superfluid. So the density, if you want the density of the total density of this helium fluid, we want to sum it up both the density of the normal fluid and density of the superfluid. So normal density of the fluid plus superfluid density. If you add it up, you will be able to find out the total density. The heat transfer in superfluid helium is very special. When the pressure above liquid helium 1 is reduced by pumping, the fluid starts boils. That is the case. So as you know, from the helium 1, temperature decreases, becomes 1. helium 1, then again further decrease in temperature, it becomes liquid helium 2. So that is obvious, it is given. The pressure above liquid helium 1, it starts boiling with respect to pumping. During this pumping, the temperature of the liquid decreases, and anyhow, a part of the fluid is boiled away from the systems. So when this temperature is less than lambda point temperatures, the boiling stops. But what condition the boiling stops? The temperature of this fluid, heat transfer temperature of the fluid, boiling temperature of fluid less than lambda point temperature, the apparent boiling of the fluid stops. See the diagram graphs 0.51, 1.52. Temperature increases, pressure also increases, density correspond. We have two density, it may be a normal density and superfluid density. So the red color line shot from the downward and upward kind of thing gives idea about density range. Normal density, superfluid density by total density, that downward system, superfluid density to total density, it is the range is available 0.2, 0.4, 0.6, 0.81. If it is increasing, the temperature increases corresponds. So this gives idea about the fluid called as superfluid helium. So superfluid conductivity is too large. The thermal conductivity of the helium 2 is so large. So the vapor bubbles, as I already mentioned, directly evaporates. It won't direct start bubbles. But here, if the 2 is it is equal to helium 1, but go for the helium 2, the conductivity of the helium 2 is very large. The vapor bubbles do not have time to form. So as I already mentioned, it directly vaporize. There is no time to form the bubbles within the body of the fluid before the system heat transfer very fastly conducted. Heat is transferred in the form of conductance. Heat conductance is very fast. So conductivity of the helium 1 is 0.024 watts per meter Kelvin, whereas helium 2 is, you see the difference, 86,500, 10,000 times higher than this, more than 10,000 times. So viscosity you see there, it is 3 to 10 power minus 6, but helium 2 is very, very low. No measurable viscosity range of 10 power minus 7 to minus 12. So normal density of the fluid is always the temperature is greater than or equal to 2.17 Kelvin. The superfluid density is equal to 0. Between 0 to 2 point, that's why I mentioned below 2.17 Kelvin, it is a no, it is a supercritical superfluid helium, liquid fluid, whereas more than 2.17 or equal to more than 2.17, it will be normal fluid. So normal fluid is more than or equal to 2.17 Kelvin. Superfluid is less than or equal to 2.17, that is 0 to 2.17 Kelvin. These are the two different fluids available with respect to superfluid and normal fluid. Super density and normal density, and total density ratio between these two correspond to the temperatures, gives the idea about the viscosity kind of thing. So everything together tends to discuss the property called as two different fluid, helium 1 and helium 2, normal fluid and superfluid, normal density, super density. Again, temperature correspond to 0.17 below, more than above 2.17 Kelvin, and all these two together termed as the liquid fluid or liquid helium, that is can be used in our various application of the cryogenic systems. So this about these are all about the background or the properties or the viscosity, density, conductivity, heat transfer, and what I call the temperature, pressures, lambda point, lambda line, the phase transition, second order phase transition, all these things together coming under the case of the fluid called as liquid helium. Apart from that, we were discussing on the TS diagram, how to fix the TS diagram properties from the TS diagram and TS tabular column data for a particular fluid known as helium. So these are all about the fluid known as what I call liquid helium. It can be used in as a cryogenic fluid, cryogenic liquid, cryogenic helium, like in terms of two fluid, normal fluid and cryogenic.